Okay. Let me get started. So today I'm going to talk about light. And, I've decided to focus an entire lecture just beginning to introduce the concept of light. One of the reasons why I think it's important to talk about light as a phenomenon in an astronomy/cosmology class is because really almost everything we know about the universe on the grandest scales basically comes from us looking at light that's coming in from us from distant objects and then squeezing information out of it. So in order to understand how we squeeze information out of light, we have to understand what light is in order to really dissect it. But I thought, because of this motivation, that gives me a little bit of an opportunity to talk about light itself as a phenomenon, because light is actually a really interesting thing in and of itself, especially in the history of science. There's kind of an interesting story associated with light. So we might ask ourselves, what is light? I mean, we don't think about it much day to day, but of course we're very much reliant on it. What we have is to take in light signals, interpret what they mean, and then allow us to function in the world. So light is bouncing off of stuff. Some of it comes into your eye, and from that, your brain tells you, oh, okay, I see a reflected thing here. Okay, there's a guy coming towards me, and I know to step back so I don't get hit. And you do all this stuff unconsciously, but it's actually quite amazing that we can do that. Well, what is this light that we rely on so much? Okay, and more generally, we now understand that light is not just visible light, the stuff you can see with your eye. There's all kinds of other light, electromagnetic radiation. That's really the same thing. The same thing in the sense that it still travels as an electromagnetic wave. It just has a different wavelength. So now we're very reliant on other wavelengths of light that you can't see with your eye. Like radio waves, longer wavelength rays are carrying information all the time. The cell phones that we all rely on so much now are just receiving signals. There's electromagnetic radiation passing through us all the time. There's radio broadcasts, television broadcasts, Wi-Fi broadcasts. All kinds of stuff is passing through us all the time, and we're relying on this electromagnetic energy for almost everything we do. So what is this stuff? And how did we come to understand it so well that now we can manipulate it and send signals and do all kinds of stuff with it? So what is light? Okay? What is it fundamentally? It's kind of hard to describe. You can only just begin to start talking about it. Okay, one of the things is it's radiation. Okay? And obviously it helps us see. Light waves carry energy, but as we know also, light waves also carry information. Light moves very fast. It moves extremely fast. 186,000 miles in a second, or about 300,000 kilometers a second. This is the distance between the Earth and the Moon, visualized here. So this is the Earth, and that's the Moon. It's not the best picture, but that's what it's supposed to be. And this is the actual time it takes for a signal of light to go between the Earth and the Moon. About 1.3 seconds. That distance is 384,000 kilometers, and it does it in almost a second, a little bit more than a second. So that's extremely fast. And in fact, it's so fast that we don't have any real conscious understanding of the speed of light. You turn the light switch on, the light comes on. Right? To us, it seems instantaneous. And I think for a lot of people, we don't even fully understand what it means for light to be traveling at a finite speed, because we think of it so instantaneously. But that's because we live on a world that's very small, and the timescales we deal with are very long, compared to the time it takes light to do stuff in our environment. So how do we begin to understand this? So if I want to know what the speed of light is, I do what everybody does. I go and type it into Google, and Google tells me the answer. But how does Google know? Or more generally, more specifically, how do all the people who made all the web pages that Google searches and does whatever it does, how do those people know what the speed of light is? How did humanity come to figure out that light moves at a finite speed? This is the most basic thing about light we can begin to talk about. And then I'll build up our information on light from there. So here is sort of a very wordy history of humanity's understanding of light. I thought I would introduce it now, and then I'll go through a small piece of it more slowly. So it's kind of interesting if you look back at, the thing we always look back to because they wrote stuff down, the ancient Greek philosophers, so Plato, for example. So Plato, around 400 BCE, suggested that your eye kind of works by emitting something. You open your eyes, okay, and some kind of visual fire emanates from the eye, somehow creates light. And then that comes into contact with stuff in the world. And then from that, you're able to deduce where stuff is. That's how you see. So obviously, if you think of that, it seems sort of bizarre now for us to think about that. But if you really think about the idea, I mean, how do you know that that's not what's actually happening, right? I mean, you close your eyes, you can't see. You open them, you can. How do you know there's not just something always coming out of your eyes that's, seeing stuff, like a tractor beam or something, Not necessarily a crazy idea. And in fact, the ancient Greeks debated whether or not light as a substance moved at all, or whether it was instantaneous. Is it just there and not there? Or is it traveling, is propagating at some finite speed? Yeah?
Wouldn't we know that that wasn't true with blind people? Because they can't see.
Well, right, but the interpretation there is there's something wrong with their eyes. Whatever it is that makes our eyes work is broken in people who are blind. And there are some people who can see better than others, and that's because their eyes work better than others. You know what I mean? You can just push back the understanding and interpret it that way. Now, not everybody thought that light was infinitely fast, so Empedocles thought that light was fast but not infinitely fast. And again, these are all philosophers. All the ancient Greeks were really philosophers. They weren't really doing a lot of, some of them did, but they weren't doing a lot of experimentation to prove their ideas. They were just kind of arguing based on logic whether one thing was true or not. Okay. But Empedocles thought that light was fast but not infinitely fast. However, Aristotle argued that light has substance but no motion. So it was just kind of frozen there. And of course, Aristotle was very influential. And in many ways, he held sway with scholars for many, many centuries. This idea that light was just there, it didn't really move, it was, it just kind of existed. Now, around circa 850, or maybe a little later, I don't know exact dates on this, there was an Arabic philosopher, Al-Kindi, who argued that vision is the result of something external entering into the eye that caused physiological effects somehow in the head, in the brain, or whatever, that allowed us to see. And many of his arguments make a lot of sense. And this was this idea that the light is external, it enters the eye, and that's how we see. Now, of course, our vision now of light is very different than this stuff that's very anthropomorphic in the sense that, when you first think about light, you're very trapped in the idea that that's what our eyes can see. Our eyes can see, it turns out, a very narrow range of wavelengths of electromagnetic light. And that's why we're sort of built up the picture from there. But if you step back now and think about what we understand about light, It's just, there's this tiny little sliver of the electromagnetic spectrum that our eyes are built to detect. And there's all this other stuff out there that our eyes can't see. But it's interesting how the story builds up based on this tiny sliver of light that we can actually see with our eyes, and it makes sense. Now, Galileo Galilei, as I'll talk about in a second, was the first person that I'm aware of, at least, who actually suggested an experiment that could be done to measure the speed of light. And what he concluded, he actually tried to do the experiment, and what he concluded is, it's too fast for me to measure. So he didn't really improve upon anything else. In 1668, this is somewhat different, but Newton discovered that prisms separate white light into many colors. So there's something about light that contains all the colors within it, at least white light does. And he began to sort of build a picture that light told us something about colors, and it's sort of a distinct set of information. We'll talk about that more in the next lecture at the end of this lecture. We now know that those colors have to do with the precise wavelengths of the light. The other thing that would become very interesting in the story of light was whether light was made up of waves or whether light was made up of particles. So do you think of light, say, coming from a lantern? Are there just a bunch of little BBs flying out of it, and light is made up of little particles that we call light particles that are just streaming all in straight lines? Or is light made up of waves, kind of like water waves, that flow? And it turns out that's a very different thing. Waves behave very differently than particles do. If you think about trying to predict what's going to happen to an ocean wave as it runs into a dock, it's very complicated. It bends around and does all kinds of stuff. But if you think about what's going to happen to a bunch of ping pong balls that are shot at something, it's much simpler. You know, some stop, some bounce, some don't. It's just a very different movement of phenomena. And around this time, people like Newton and these folks were trying to figure out whether or not light is moving at a finite speed or not. Does it travel like a wave, or does it travel like particles streaming along? Fundamentally, what is it? 1680 was, around 1680 was the first time that someone actually was able to measure the speed of light. So it's very it's amazing actually that in the 1600s, Romer, an astronomer, a Danish astronomer, was actually able to provide a very good determination of the speed of light. And I'll spend some time explaining how he did that. So they didn't really even have clocks. They had clocks, but they didn't have very good clocks at that time. So this is amazing. And I'll talk more about these things later. I mean, there's an evolution of other things we learn about light as time goes on. But I want to go on now to begin introducing this point of Romer actually measuring the speed of light, how that led to a deeper understanding in the future. So as I mentioned, Galileo was the first person to try to conduct an experiment to measure the speed of light. So what did he do? So the idea is he had an assistant. And him and an assistant went out and they each had lanterns. Right? So they took these lanterns, they're big bright lamps, and they both went out in some big field very far away from each other. Okay? And the idea was they would know how far away they were from each other. Let's say they go off exactly a mile away from each other. Okay? And the idea is that if they can measure the time it took light to travel between one lantern and the next lantern, then they can measure the speed of light. Because the speed of something is the distance that it travels divided by the time it takes to travel. So if they know the distance between these lamps, say a mile, and if they measure the time it takes for light to travel from one lamp to the next, then they would know the speed of light. Okay? So this was the idea. So how did they do this? So Galileo's idea was, okay, let's cover our lanterns up. Okay? Cover them up with some kind of shades. And then I'm going to take my lampshade off and I'm going to start my stopwatch. Okay? And the light from my lantern then will go to you. And then as soon as you see the light, you take your lampshade off. And then your light will come on, and I will see how long it takes for me to see your light. So if I can measure the time between when I take my lampshade off and when I see your lantern, that'll be how long it took for light to travel between me and you. Back. Does that make sense? Now, a couple problems here. First of all, he did not have a stopwatch. Okay, he had probably a pendulum clock or maybe a water clock. I wasn't able to figure out what kind of clock he used. But the best clocks at the time were these pendulum clocks, which were not great clocks compared to what we use now. And what he concluded is, as soon as he took his thing off, he saw his partner take his thing off. Like it was instantaneous. So the only thing he could conclude was that light was at least 10 times faster than sound. Because he concluded that if it traveled the speed of sound, he could have done it. You could measure those time differences. And he realized that his clock was not good enough to discern the difference between the time lag. So that was his conclusion. Light is at least 10 times faster than sound. Okay. But at least you tried, right? Now, why didn't this work? Well, we know now that light travels at a speed of 186,000 miles in a second. So if this distance is 1 mile, and the speed is 186,000 miles in a second, and we can figure out what time you would need to have this divided by this equal 186,000. Okay. So the time required then would just be the distance divided by the speed. I play with this equation. So the time would be 1 mile in 186,000 miles in a second. That's 5 times 10 to the minus 6 seconds. So that's 5 1/millionths of a second is how long he was trying to measure with a pendulum clock. So that would be hard. You couldn't even do that with a really good, stopwatch. You would need like an atomic clock or something. So it's no wonder that Galileo was not able to do it. So how do we get times that we can measure? Okay, what could we do with this experiment if we could, in order to actually measure the time delay? What would we have to do? What would we have to do about the distance between the lanterns, for example? Yeah, that would be much, much, much bigger. Okay. So if the lanterns were 186,000 miles apart, then you can measure the second, the 1 second it took for the delay. So you need really, really big distances to do this. Okay. Now the most natural place to look for these distances are like the separations between the planets. Okay, that's the kind of distances we're talking about for this kind of thing to matter. It turns out that we now know that it takes light about 8 minutes to travel from the sun to the Earth. And so that gives you a sense of the sort of large distance scales we're dealing with. So the first person to do this was Romer. And the sort of context of this was that in 1625, Christian Huygens had this hypothesis that light moves at a finite speed. And in fact, Romer was aware of this, but in fact, Huygens never actually did an experiment to promote it. He just sort of said, it must be true that it travels at a finite speed, and then he kind of worked stuff out based on that assumption. About the same time, Descartes, the famous French philosopher Descartes, was trying to make strenuous arguments on the other direction. So he tried to make logical arguments that, look, light is instantaneous, it transmits instantaneously. A lot of famous physicists tried to convince Descartes that he was wrong. But in fact, he was such a powerful philosopher at the time, such an important philosopher that sort of the educated masses kind of believed everything he said, that he really delayed the acceptance of even Omer's measurement of the finite speed of light. So this is Romer in 1676. And what he did to deduce the speed of light was he was studying Io, the moon of Jupiter. So that's the inner moon of Jupiter, this one right here. Now Jupiter's very far away, and so we've already got a far distance to play with. So that was the first step. Now, this is a movie of Io going around Jupiter. And now it's in eclipse, and now it's back. So what's going on is Jupiter's here, and Io's going around it. And when Io goes behind Jupiter, you can't see it anymore. It's being blocked. It's dark. Okay, so there's Jupiter. And when Io goes around it, it gets dark. Because we've already seen that. So the basic idea is, here's Jupiter, here's Io, and Io's orbiting like this. And what you can do is you can see, okay, I can see it in my telescope, I can see it in my telescope, then it goes behind Jupiter, you can't see it anymore, and then it comes back out. Okay. And Romer was studying this. And one of the reasons why they studied this at the time was that Io goes around Jupiter every 42 hours or so. So it's actually kind of a nice clock. People wanted to treat it like a clock because they wanted to be able to time things very precisely, and they wanted to treat Io like a clock going around Jupiter. But Romer noticed something kind of weird. He noticed that depending on what time of year it was, sometimes it took Io longer to get back from the dark side of Jupiter. That is, sometimes it was eclipsed for less amount of time, and sometimes it was eclipsed for longer. So sometimes it might take, a couple hours for it to come out, and another time it might take 2.5 hours for it to come out the other side. So the time it was spent in eclipse seemed to change, depending on what time of year it was. And this was bizarre to him. What is going on? Like, shouldn't this thing just keep orbiting with the same rate according to Newton's laws? It ought to do this. I mean, what's up? What he said is that the Earth's distance to Jupiter changed over the year. And that was part of what was going on. So specifically, what he said was, this is actually an image from his paper where he tried to deduce this. He said that when the Earth was moving toward Jupiter, okay, so this thing up here is Jupiter, and this is the Sun, and this is the Earth going around the Sun. So he said, when the Earth is moving towards Jupiter, it looked like the orbital period of Io was shorter. That is, it didn't take as long for him to see the other side, it come out the other side. But on the other hand, when the Earth was on the other side of the Sun, going away from Jupiter, it seemed to take a little bit longer for Io to emerge from the shadow of Jupiter on the other side. Okay? And what he said was going on is, Io goes behind Jupiter, and in the meantime, the Earth moves forward in its orbit. And so then when Io comes back out from the other side of Jupiter, the light from Io doesn't have as far to go as it did. But on the other side, since the Earth is going this way, it disappears behind Jupiter, and then the Earth moves a little bit, and now the light has farther to go. So it's going to take it a little bit longer. And so this is the idea. So imagine this is Io in the shadow of Jupiter. So this blue is supposed to be the shadow of Jupiter. This is Io. So path B from here takes longer than path A, because path B is a little farther away. Similarly, when Earth is moving in the other direction, path D is shorter than path C, which would be this one. That was his argument. All right, so that's what he said. And the conclusion then was that light must be moving at a finite speed if I can detect this distant difference. And he knew the distance, he knew the difference in distances, and from that he was able to effectively deduce the speed of light. And in fact, a few years later, Newton wrote in his famous book Principia, he basically assumed that this was true. And then what he said is, for now it is certain from the phenomena of Jupiter's satellites, confirmed by the observations of different astronomers, that light requires about 7 or 8 minutes to travel from the sun to the Earth. And that's basically correct. So in the 1680s, Newton and the people studying astronomy at that time had known the speed of light, this incredibly fast speed following this argument. Now, what's really cool about this story is that in September of 1676, Romer made an announcement to the French Academy of Sciences and basically said, hey, Io is going to be eclipsed by Jupiter, and you can predict when you think the next eclipse should happen, because we all know how fast Io is going around Jupiter. But I'm here to tell you that it's going to occur exactly 10 minutes later than you all compute it will. So the eclipse is going to happen 10 minutes later than you think it will. Because he knew this phenomenon of distances, and they didn't. And he kept making a big deal about this prediction, because he wanted to get attention. He kept sort of putting it in their face, like, this is going to happen, you measure it, I'm telling you this is going to happen. And he said, if this happened, that the delay would arise from the simple fact that astronomers considered light to be propagated instantaneously rather than gradually. So this was the language they were using at the time. They did the observation, they confirmed that he was right, and basically this was the point when people really started believing in the idea that light is moving at a finite speed, not an infinite speed. Turns out that he got the speed a little wrong. He said it would require 22 minutes to go from one side of Earth's orbit to the other. The real answer is 16 minutes. But that's still pretty good. And then a few years later, it was refined. So the history of this then is that in 1809, a French astronomer named Jean-Baptiste Delambre increased the precision of this, eventually measured the speed of light to just over 300,000 kilometers per second, which is pretty close to the right answer. There have been increasing precision in our ability to measure the speed of light with more complicated techniques over the few years. Current technique involves cavity resonator waveometers, as they're known. And basically, we now know the speed of light to a ridiculous precision by really taking into account the wave nature of light. We now know the speed of light is 299,792.5458 kilometers per second. So now, sorry?
What does the machine do now?
So basically, it takes into account the fact that light is a wave, and so it turns out with waves you get so waves can interfere with each other. So and I'll talk a little bit about this later. Like if you have two waves that are coming at each other, if the crest of one wave overlaps the trough with another wave, they can interfere. And so if you set up like a series of mirrors such that you have a light wave coming in and another light wave coming at it by bouncing back and forth on mirrors, it turns out it's pretty easy to measure when this cancellation happens, when this complete cancellation of crest on trough happens. And so what you do is you can very finely tune the distance between mirrors to get this cancellation to be perfect. And then you can know exactly what the distance between the mirrors is. And by understanding exactly how this cancellation happens, you can put really tight constraints on the velocity of light. So I guess the broad answer is it has to do with really understanding the wave nature of light and taking into account that detail in order to back somehow. These were techniques that were basically invented in the 20th century to try to really nail down aspects of light. Yeah?
What happens when they go together? Does it just...
It cancels out so you get a dark spot. So and I'll talk about this a little later, either today or tomorrow, or Thursday. It's kind of like, it's kind of like if you have a big ocean wave and another ocean wave is coming at it. Okay, maybe you've seen this kind of thing in the ocean or in a swimming pool or something. If you have a high wave like this and a high wave that's coming like that, and those two waves cross, you'll get a really big wave. Okay? But if the waves come at each other with the timing being off, you actually get points within that wave, within that wave distribution where the water is perfectly smooth. So what happens is, the light cancels itself out, and you would get effectively darkness. So if you had light shining on a wall, and then you had another beam of light that was appropriately tuned so that the wave fronts were canceling each other, you would get dark. You can get a series of light and dark spots on the wall. And I'll show you pictures of this with actual real experiments. But it's actually pretty fascinating. And this aspect of light was part of sort of frontier research in the early 20th century when people were beginning to really convince themselves that light was a wave. Yeah?
What kind of experiment did the Lombre use to find out that
Oh, he also used exactly the same thing. So he used this Moons of Io exactly the same way that Romer did. He just did it with better observations. Yeah?
Does lighthouse interference from like the atmosphere or just interference with light itself?
Yeah, light's interfering with everything. So, yeah.
Does it slow it down?
Yeah, so it turns out that light through in a vacuum, in complete empty space, travels at this speed. But when light travels through other things, the speed is a little bit different. So light through air is just slightly slower than light through empty space. Light through water is a lot slower than light through air. And it turns out that the fact that light travels at a different speed in water and in air is responsible for sort of a lot of phenomena that we're sort of used to seeing. Like, have you ever stood in a swimming pool and you look at where your feet are compared to your torso, and they're like displaced? Or you look at your friend and like your friend's body's here and then all of a sudden the feet are over there. You know what I mean? Like there's that weird thing you get when you look in a swimming pool. That's because light is traveling at a different speed in the water and in air, and that effectively makes the trajectory of light bend a little bit as it comes out of air, as it comes out of the water into air. That's because of the wave nature of light. That's called refraction. Light also travels at a different speed in glass than it does in air, and that's why lenses work. So that's why your glasses work the way they do, your contact lenses work the way they do. The fact that light travels at a different speed in glass than in air means that it will tend to bend a little bit if it goes through glass that's slanted. And that understanding how light bends when it goes through glass is how we make lenses. And all of this comes down to the fact that light travels at a slightly different speed in some materials than others. So what is light? So now we've sort of come to convince ourselves that light travels at a finite speed. And people, in the 1600s were beginning to understand that light does indeed travel at a finite speed. They did not know, as we know now, that light travels as a wave. What we now understand is that the light we know about is actually, the visible light we know about is actually just part of a very broad spectrum of electromagnetic radiation that runs from gamma rays, X-rays, ultraviolet rays, of course visible light, and then infrared light, TV, radio, etc. All of that is all light. And it all behaves in a general sense just like light does. The difference between these different types of light is the wavelength. And specifically what I'm talking about wavelength is, you can characterize it as if you have a wave that has a series of peaks and troughs, the wavelength is the distance from peak to peak. So if you imagine a wave that I sort of sketched in the room like that, okay, its wavelength would be about that big, about a meter. So this is a sketch of the electromagnetic spectrum, which runs from gamma rays all the way to radio waves. Now, just to clarify, the names we give to the different pieces of the electromagnetic spectrum are sort of made up. They're just based on usage and historically why they came about, how they were originally measured, etc., etc. But basically, the very short end are gamma rays. Okay, the very shortest wavelength light is gamma rays. and they have wavelengths of something like 10 to the minus 14 meters, very, very small. The visible light has a wavelength of somewhere around 5,000 angstroms, and an angstrom is 10 to the minus 10 meters. Okay? So it's something like 5 times 10 to the minus 7 meters is the wavelength of light that we see with our eye. That's very, very small. And then as you go larger wavelength light, you go into infrared, radar, and then finally radio. Why is it called infrared? Well, the longest wavelength visible light is red, and the shortest wavelength visible light is what we see as blue or purple or violet. So shorter than violet is called ultraviolet, and longer than red is called infrared. That's where those names come from. And depending on the wavelength of light you're dealing with, it interacts with matter in a different way. Okay? So the really long wavelength light, the radio waves, they're so big that they basically go through small stuff. So radio waves are going through us all the time, right? It doesn't really affect us very much. Gamma rays also go through us all the time. Well, not all the time. They can go through us. Gamma rays can go through us. But it's a little bit more unpleasant because they're so small that they basically go right through, but in a bit more caustic way. Okay. Now, this began to be deduced, again, going back to Newton, when Newton was studying what prisms do when white light goes inside of them. So when white light goes inside a prism, the prism effectively spreads the light out. And the reason this works is it turns out that, well, the way in which light travels through the glass in a pendulum, in a prism, depends a little bit on the wavelength of the light, and that's why the light spreads out. It goes through. But you see this when white light goes through a prism, it actually gets spread out into its constituent colors. So violet light has a wavelength of about 4,000 angstroms, and red light has a wavelength of about 6,500 angstroms. Now the other thing that's important to know about waves, okay, is that there's a relationship between the wavelength of the wave and how fast the wave travels. Okay? Now, imagine you have an ocean wave that's going by that has some wavelength. And imagine I've got some kind of clapper in the water that whenever the wave crest goes by, it claps. Okay? Now let's say the wave is traveling at some speed. Every time the crest comes by, it'll clap. Okay? And there's a frequency of that clapping. There might be a clap every 2 seconds. Okay? So the frequency of that wave is 2 hertz. Okay? 2 per second, say. That would be 2 hertz. So a hertz is per second. So if it does it twice per second, the frequency is 2 hertz. All right? And as I change the wavelength of the wave, as the crests get farther and farther apart, if I keep the speed the same, that's going to change the frequency. So as I make the wavelength larger, the frequency is going to go down. So now it might only be 1 per second rather than 2 per second as the wavelength gets larger. Similarly, if the wavelengths get smaller, then they'll hit my hand more rapidly. So the frequency would go up. So there's a relationship between nu, which is the frequency of the wave, and the wavelength of the wave, such that when you multiply them together, you get the speed with which the wave is propagated. Now, one way to understand this is that speed has units of distance per time, or say meters per second. The wavelength has units of meters, and frequency has units of per second. So you have something that's meters per second, you get something as units of speed. The reason why I'm spending so much time on this is light moves at a speed, the speed of light, 300,000 kilometers per second. So whenever you take a wavelength of a light and the frequency of the light and multiply it by themselves, you always get the same number. It's always the speed of light. What this means is if the wavelength goes up, the frequency has to go down. If the wavelength goes down, the frequency has to go up. There's a one-to-one relationship between the wavelength of the light and the frequency of the light. It's the same thing. Now, depending on what context is, some people will describe light in terms of its frequency, and some people will describe light in terms of its wavelength, but it's equivalent. So on your radio dial, okay, what is generally used to describe the electromagnetic radiation that we're reading in as radio waves? It's the frequency. Okay, so it might be so-and-so megahertz. Okay, such and such megahertz frequency. Okay, megahertz is a unit of frequency because it's a hertz. All right, and those numbers on your FM dial and on your AM dial correspond to the frequency of the electromagnetic radiation that you're reading in. So sometimes you'll hear electromagnetic radiation described as a frequency, and sometimes you'll hear it described as a wavelength. Typically, the longer wavelength stuff, there's just a rule of thumb that people characterize it by the frequency, and the shorter wavelength stuff, they characterize it by the wavelength, but it's all the same thing. Okay. Now, so are there any questions about that? I just wanted to give you kind of an introduction to what it is, and we deal with it normally. I just wanted to clarify a few things. Are there any questions about that? Like the electromagnetic spectrum, what it is we're talking about? Okay. Now, I've been telling you all this stuff as if the story of light is now cut and dry, we understand everything about it, and we're done. Okay. But it turns out that in the early part of the 20th century, it was eventually realized that light behaves in a totally foreign way than almost anything else we know of in the macroscopic world. So, what I mean by that is, it's not correct to think about light as traveling along like a stream of little balls that are just kind of like flying out of one of those t-shirt guns or something. One thing it does is it travels through space like a wave, and I'll explain what that means later. But it propagates in the same way that a wave propagates. Like I was mentioning before, if you think about how ocean waves travel along and interact with stuff, that's a lot different than the way that balls flying through the air travel along and interact with stuff. But when light hits things, it interacts with things, interacts with matter. It does that like a particle. And that's a very weird thing. Let me sort of build up as to why this is so strange. Now, one of the things that we know about how waves travel in general is they do things like they refract. Okay, and what is this? This is what I was talking about with the whole swimming pool thing. You see somebody in a swimming pool, they look disjoint. Or sometimes, like, if you look through glass, it'll look, your picture of what's going on the outside will look a little funny. Okay. And the reason why this happens is because light is traveling at a different speed in air as it does in glass. So what happens is you have wavelengths that are coming in to glass, and when the bottom part of the wavelength hits the glass, it slows down. But the top part of the wave doesn't slow down until it hits the glass, and what that effectively does is it makes it turn. And then the opposite thing happens when the light wave exits the glass. So the first bit of the wave that exits the glass starts to speed up, and then the stuff that stays inside the glass doesn't, and effectively that turns it back. So you get this kind of dislocated kind of positions if you look through glass or you look through water or whatever. People know what I'm talking about here?
Yeah.
Okay, good. That's a phenomenon of waves. Waves do that. Okay? If I was firing a shotgun into the water, right, the little pellet would not do this. It would just go straight. Right? So if I had a bunch of BBs traveling to the water, that would not happen. This is what waves do. Sound waves do the same thing. The other thing they do is they interfere with each other. This is what I was talking about stuff overlapping. Okay? Now, you can kind of see that in a picture here of water waves. What's happened is someone's thrown a pebble here, someone's thrown a pebble here, and waves have propagated out from the points where those pebbles have landed. And you can see the points where those rings of wavelets overlap with each other. You get really high wave crests. And there are other points where high points in this wave will overlap with the low point in this wave, and then you just get perfect flatness. And the way to visualize that is, if you have, a wave that looks like that with wave crests, and it lines up with the trough of this other wave, you can just take the height of this one, add it to the depth of that one, and you get something that's very minute. So you can envision if you have two waves where the crest of one is aligned with the trough of another one, you get a very flat kind of result. Something similar to this is like, have you ever been bouncing on a trampoline with someone, and then you time the bounce, you get really high? It's kind of like that. Okay. If you time that bounce right, you get totally bounced up high, because it's kind of like a double wave. But if you time the bounce wrong, then it sucks, and you both kind of don't. It's the same kind of idea. And that's a general phenomenon of wave activity. You get that in waves. You get that in water waves. You get that in sound waves. You can try to have sound-canceling headphones that cancel out the sound from the outside. They try to work on that kind of technology. You can cancel out sound, but if you get it to bounce around and cancel itself out. The other thing that waves do is they exhibit the Doppler effect. All right? And the Doppler effect is the thing that makes, if you're standing on a corner and a car is coming, the sound, loud engine, will sound high-pitched coming at you, and then drop in tone as it goes away. Like, meow, high pitch and then low pitch as it goes away. That's because as the car is traveling towards you, right, it's emitting these sound waves. Right? So imagine that I'm an engine and I'm emitting sound waves in these spheres that go out. So sound waves are just pressure waves in the air. That's what they are, but they're just waves. Just think about them as concentric spheres. And if the car is standing still and your ear hears it, you'll just hear a constant, constant vibration. But if the car is traveling towards you, okay, it emits a sphere, and then it moves toward the near edge of that sphere, and then emits another one. So what happens is the sound crests pile up towards each other in the direction that the car is headed. And when they pile up towards each other, that means the frequency goes up. The frequency of those crests hitting something goes up. So that's a high pitch. The frequency of your eardrum vibrating is a high pitch. It's a high frequency. If it's a low frequency sound wave, your eardrum vibrates at a lower frequency and you hear a lower pitch. And so that's what's happening here. So this person's on the far side of the car. They're seeing very large distances between the crests, so they're hearing a low pitch. This person's in the near side of the car that is traveling towards them. They're hearing a high pitch. So that general effect is called the Doppler shift. The tendency for waves to be blue shifted or wavelength effectively shortened in the direction that if they're traveling towards an observer. If you're traveling away from the observer, the wavelength is effectively stretched. And light exhibits that too. So you can observe that. That's actually, it turns out, we observe that effect all the time when we study distant objects in the universe that are moving around each other. That's one way you can measure how fast things are spinning around each other in the universe, because we rely on this redshift. Are there any questions about that? Okay, so we're familiar with these things. I mean, you actually encounter these things all the time. The wave interference a little less so, but certainly the Doppler effect, you encounter it with sound all the time. And the wave refraction, you see it. You use it with lenses and stuff like that every day. light travels like a wave, okay? That's why this straw is like that, okay? That's why if you're trying to pick up a key on the bottom of a pond, you don't reach straight at it. You think it's there, but really it's there, the other way around. That's what this is supposed to be. Light does that, okay? Light also interferes with itself. So you can send light through two slits, and you can create interference patterns on walls. Okay, so there are experiments that we have in the labs here, where if you have a couple little slits where you emit light from, that light will interfere, light from two different sources will interfere with itself in such a way to create a series of bright and dark spots. That's a characteristic pattern of interference of light waves. Okay, so you have light, it's coming through two slits. Light emits from those slits. The light travels in a specific distance to one point on the wall. It'll positively interfere and make a spot that's very bright. A spot right next to that on the wall will get very dark, etc., etc. You'll get a series of bright and dark spots, right? That's just a phenomenon of light. And in fact, you can use that to measure wavelengths of light. Okay? All right, fine. Why do I care? You might not be that interested in that. I'll tell you in a second. So light also exhibits a Doppler effect, as I've said. But there's another thing that light does that totally flies in the face of this. Okay? And this thing was a puzzle to people around the year 1900. Okay? Now here's the deal. There's this famous effect that was known in experiments at this time called the photoelectric effect. That if you take light and you shine it on metal, if you take certain light, say blue light, and shine it on a metal, eventually electrons start popping off of the metal. So what's happening is there's the metal, it's somehow absorbing energy from the light, it's heating up electrons, the electrons are popping off. All right? And but it turns out that if you change the wavelength of the light to a longer wavelength, then the electrons no longer pop off. They just stop popping off. What's more, the speed with which the electrons pop off are totally independent to how bright the light is. That is, you can make the light 1,000 times brighter as long as it's the same wavelength. And the speed with which each electron is flying off the metal doesn't change at all. So you might think that if you shine a really bright light onto something, you're depositing lots and lots of energy, stuff ought to fly off at like popcorn popping off. It ought to pop off at a higher speed. But that's not seen. Now it turns out this is an immense puzzle to classical physics. If you treat light as a wave, this should not happen. Now, around this time, there was a guy named Einstein who was a new PhD student whose professors all hated him because he was kind of a wise ass, so he couldn't get a job. And he ended up working at a patent office, but he was reading the physics papers. And he had a crazy idea that might explain this. He said, well, if light is not a wave, but if light is composed of particles, and in fact there's particles traveling along here, and each particle of light hits an electron and knocks it out in a one-to-one way. And the other thing I'm going to assume is that depending on the wavelength of light, that dictates what the energy of each of those pieces of light has. So these pieces of light we now call photons. And the idea was the longer the wavelength of light, the lower energy each photon was. So if you have long wavelength light, the photons are not very strong, and they can't knock electrons out. But shorter wavelength light, the photons are very powerful, and they can knock electrons out. And therefore, the speed with which the electrons fly out, which is characteristic of the energy that they got, ought to depend only on the wavelength of the light, and not on how bright the light is or anything else. So that's what Einstein suggested. So what he said is that light deposits energy in quanta. It's not continuous like a water wave or a sound wave or anything else. We now call these light particles photons, And the energy of the photon depends on the wavelength. Now, Einstein is the same guy that brought you E equals mc squared and relativity, this idea that there's something called time dilation that I'll talk about later in the course, length contraction, a lot of weird stuff Einstein suggested, turns out at about the same time. And then he also suggested that light travels like a particle, that light hits like a particle. At about the same time, he was coming up with all these ideas. When this happened, the thing he was most nervous about, that he thought was probably the craziest idea, was this idea that light deposits its energy like particles. Because this flew in the face of all of this research on wave-like behavior of light. In fact, he was convinced on the other stuff. He's like, I know E equals mc squared, I know that's right. But this, he said, now this is crazy, this takes some guts to put this out. But I'm young and I've got a lot of guts, I'm going to put this out. Turns out that sometime later, Einstein got the Nobel Prize. But what a lot of people don't know is that Einstein did not get the Nobel Prize for E equals mc squared or all that other stuff. He got the Nobel Prize for this. This idea was sort of the beginning, or one of the founding pieces of thought that contributed to a field of theoretical physics known as quantum mechanics. Quantum mechanics now, we think, is the physics that governs everything in the microscopic world. It's fundamental for the development of a lot of electronics, like transistors, and a lot of things that are going on today in the modern world. And it was really this insight, this kind of crazy idea, that light sort of has a dual nature. That it travels like a wave, it refracts, it does the Doppler effect, it does all this other stuff, but it deposits energy like individual particles. That was sort of one of the first steps of quantum mechanics. So that the shorthand way of saying it is light travels like a wave, but it hits like a particle. Interestingly, so this is called particle-wave duality. Who's heard of particle-wave duality? So this phenomenon is called particle-wave duality, and it's actually a very weird thing. And it's something that people who do philosophy of science spend a lot of time thinking about. And it's something that professional physicists also spend a lot of time thinking about, but they don't tell anyone. Because we're supposed to accept that it's true. The reality is that there's a very well-developed theory called quantum mechanics and its extensions that works. It explains every single observation that's ever been done to test it. So we think it is an accurate description of the world. But it's very weird. Okay? And it's intimately linked with the theory of quantum mechanics in the sense that we actually now think that everything, all particles, have a particle-wave duality. That electrons, even though we think of them as particles, actually have a wavelength. And they don't behave exclusively like particles. They have a wave-like behavior. In fact, this whole idea that there are energy levels in atoms, that you've probably all studied, you've studied energy levels. Okay? That's fundamental to quantum mechanics. The way those elements arrange themselves in the periodic table is fundamentally linked to the idea that particles and waves, particles have a wave duality, as it will. Let me explain to you one of the very weird things about this particle-wave duality, and then I'll be done. So, if you do this experiment, and you shine light through two slits, the light will go and project on the wall, and on the wall, what you'll get is a series of bright and dark spots. And this is because some parts of the waves overlap in crests, and other parts of the wave overlap with crests and troughs, and they cancel each other out. This is a well-known phenomenon. And it turns out you can do this experiment, you can start to slow the sort of rate with which photons go through the slits down. Okay? So imagine now I slowed my light source down such that only one photon is coming out per second. Okay? So the photon goes through. Now look, it's got to pick a slit to go through, right? It's only one photon. It's either go through this slit or this slit. And you turn the machine on, the photon goes through, and you see it hits the wall. It goes, hits the wall. Then the next photon goes through. One photon. Comes through, it hits the wall. It hits here. You let this go, you let it build up for an hour. And after a while, a pattern emerges. And it's not uniformly sprayed across the wall. It's hit here, it's not hit here, and there, and not hit there. This is a very weird thing. If I had two slits, and I just had a tennis ball gun, and I was just firing it at the wall, at those slits, then it wouldn't do that. The tennis ball would go through one slit, or go through the other slit, and just go all over the wall. That's not what happens. Particle by particle, this happens, as if they interfere with themselves. There's something about the way that particles propagate, that they have this wave-like phenomenon that effectively they interfere with themselves when they travel. And this has been seen. Electrons do the same thing. You can build an electron gun and fire electrons through slits. As long as those slits are appropriately spaced, you get the same effect when electrons go through slits. And that's one reason why we think electrons have wavelengths. Okay? So, it does seem like this phenomenon exists, it's universal, and it's fundamental. And as we'll talk about next time, we're very lucky that light has this behavior. Because light has this quantum mechanical behavior, it carries with it information. When we look at light of a given wavelength, all its photons have a given energy. And what that means is they can interact with certain kinds of things well and can interact with other kinds of things not so well. So, and this leads into the science of what's called absorption lines of spectroscopy that allows you to study light coming from something and figure out what that thing is made of by disentangling the wavelength distribution of light that's coming from it. Okay, that's it. We'll see you Thursday.